So, if you recall from yesterday, we were right in the midst of calculating our first average atomic mass from percent abundance information. I was about to ask you, and I may or may not have actually gotten to the question yet. And it doesn't matter because we didn't finish it, obviously. What does this value represent? The mass number. What is the mass number referring to? Particle in the nucleus, which is protons and neutrons. What is the relative mass of a proton? 1. What is the relative mass of a neutron? 1 AMU. Therefore, if there's, well, how many protons are there? 17. And therefore, how many neutrons? 8. This is so funny to watch you guys try to do the math there. There's 18, okay, which adds up to 35. And in chlorine-37, how many protons? 17. How many neutrons? 20. That means 37. So the mass should be 37 AMUs. Good look there, Mason. If anything, shouldn't the mass be slightly higher than 35 and 37? Because what are we not considering yet? The electrons. But remember, we've already determined these electrons are really less than 1,000, or about 1,000th of the mass of each of the other particles, so, you know, that's not going to influence that time. But what seems to be the issue here? It's less than the sum of the particles, the masses of the particles. So it's like taking the mass of each of these books, multiplying it by 10, and coming up with a mass less than that. This doesn't bother you guys at all. You're okay with that. Why is that? It's easier to not ask questions. This doesn't bother any of you. Okay, well then this is a great opportunity to learn something, but apparently we don't care, so we're going to move on. Eric, do you care?
Sure. I do.
You care? Just a little bit.
Well, I want my brain
1 plus 1 is 1.7.
It's making me think that we rounded it, but like...
How do you round 17 plus 18?
That is true.
How do you round 17 plus 18? Here's what I would like to happen. What is in the nucleus? Everyone together now. Protons and neutrons. Are any of those particles charged? I should have recorded yesterday's class, my 9th period class, because they were like just flat out stunned and just boggled, and I should have recorded them. Anyway. Protons and neutrons. And we said the protons are charged. What is the charge? Do they like to be near each other? Protons. I can clearly see that. Do like charges prefer to be next to each other? They want to get away from each other as much as possible. What types of charges do want to be near each other? Opposite charges. Do electrons like to be near each other? This is really actually this whole concept of like charges repelling and opposite charges attracting is going to be our whole next chapter. I mean, honestly, it's our whole next 4 chapters. Well, to kind of demonstrate what I'm about to show you here is I could have all the young men stand up, and I would like you all to squeeze and get yourselves as close as possible into that little corner back there. For the 3rd time in my career, they're actually going to do it. I've never seen this before until... Stop, don't. Oh my gosh. Oh my gosh. Come back. You guys are actually going to do it. I should have just let them go. And see how close they would have actually gotten to it. Are you guys freshmen? Because it's only freshman boys that like to touch each other. You guys are going to do it. Okay, up until this moment, only one other time in my entire 26-year teaching career have I actually had the young men get up and go into the corner and get together. Usually, everyone looks at each other like, yeah, right. Because typically, unless you're a freshman boy, you don't like to be near other boys that much. I was trying to get you guys to be like protons that don't want to be next to each other. Yeah, you're more than welcome. Anyway, this moment's kind of lost now. I don't know what to think here. Well, let's go back to the thing that you may or may not be aware of, that positive charges don't like to be near each other. Yet, here they are. Now, you don't have to draw this, because I'm sure you've seen this before. In fact, you've probably drawn one of these before. But are you guys somewhat familiar with representing an atom with something, a picture that looks something like that? Okay, so that's an incredibly disproportional arrangement of the areas here. What is this little area representing? That would be representing a nucleus, and this is obviously the energy levels, the electron cloud, blah, 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 right? Okay. Now, in order to make this proportional, there we go. You guys see that? Right, okay, and that would be closer to the actual size relationship between the nucleus and the rest of the atom. The nucleus, as you guys read through some of the questions, is incredibly small. Yet, that is where nearly all of the mass is, in a really tiny area. What is the rest of the atom? What's that? Empty space. It's okay. It's fun to contemplate. There's a whole can of worms there. I mean, I'm currently standing on empty space. You're currently sitting on empty space, mostly. Yet this empty space is supporting you. Isn't that cool? Okay, anyway. Now, here's the problem I have with representing a nucleus like that, is because you guys have just left biology here somewhat recently. You guys are used to something called, well, is there a nucleus in a cell? Right. And what's inside of that nucleus? A bunch of stuff. And what's keeping all that stuff in there? No. The nuclear membrane. Was that you? Nuclear membrane, right? Well, here's the problem I have with drawing an atom like this, because it implies that there's a structure keeping the protons and neutrons together. I don't know if that thought has ever come across your mind. I've had students in the past think there's a structure that's keeping the protons and neutrons in the nucleus. There is not. Okay? All of these things, so I actually prefer to draw a nucleus like this. I like to draw like little things representing protons, and I like to draw little things representing neutrons. Okay. I like to do it like that because that's showing you that there's just particles that are together. except for this particular class, do those little blue things really want to be next to each other? Flat out, no. They're trying to get as far away from each other as possible. Yet here they are, jammed into such a small space, right next to each other. How could that possibly be? What would be required to keep those things together? The electrons. Those things are so far away.
Something with a negative charge.
Well, the only thing with negative charges are electrons.
Okay.
And again, what are the three subatomic particles? Protons, neutrons, and electrons. The electrons that are existing are, well, they're way outside. They don't have anything to do with it. Have you ever heard? Yes?
I have no idea what it means.
Good.
It's a strong nuclear force.
Okay, excellent. Thank you that you don't, thanks for, I have no idea what it means, but you've heard of it. I have yet to run into a class in which at least one student has not heard of either the weak or the strong or nuclear force. Have you guys all heard of such thing, right? Now the question becomes, where does this force come from? In order to keep all of, except for this class, in order to keep all of you guys together, what's going to have to be used to put all of you together? Energy, perhaps? Would it require some energy to pull some people together and push them together and keep them together? Things that don't want to be together. Does anyone have... no, you're... Okay, forget. So, where's this energy coming from? To supply energy for this force, a strong nuclear force, where's this energy coming from? Okay, well, there's this relatively obscure scientist that very few people have ever known that actually created this equation. Has anyone seen that equation before? Does anyone happen to remember who was responsible for that equation? Some relatively obscure guy named Einstein that came up with this equation. Does anybody know what any of these things mean? Energy, excellent. Mass, and, don't say the speed of light. The speed of electromagnetic radiation in a vacuum. That's all of next chapter. Not all of it, but a lot of next chapter. What's that?
That's what we talked about yesterday's physics.
Okay, you're going to see how this... So you actually knew this. You knew the answer to this all along. You just never put it together. Okay? This is a constant. C is a constant because it is, like I said, the speed of electromagnetic radiation in a vacuum. Now, what are types of electromagnetic radiation that you guys are aware of? Actually, we're diving into Chapter 4 here a little bit. What's that? Microwaves? UV? Gamma? X-rays? Visible light? Radio waves? You see, infrared? Look, you guys are aware of all this stuff, right? All of these types of radiation travel at exactly the same velocity in a vacuum. Now, where would one find a vacuum? Throughout most of the universe. Most of the universe is a vacuum. Okay, so as these forms of energy are traveling through space, they're moving at a certain velocity. As anyone, you probably know now since you did this in physics yesterday. What is that velocity? Do you know? I'm sorry, what? Okay. You weren't there. 2.9979 times 10 to the 8th meters per second. Were you going to say that? Okay, but anyway, it's a constant. Therefore, it's the thing that relates these two things together. So, I can do something like this. Does anyone ever see that sign before? Does anyone know what it means? Who said that? The proportionality symbol. So that means energy is proportional to mass. And the way the equation was written before it was set as equal to each other, that means energy can be transformed into mass, and mass can be transformed into energy, which is where you were headed a little bit, okay? So, let's think this through. What do we need to keep all these positively charged particles right next to each other? We need some energy. Where are we going to get that energy? Oh, we could use some of this mass to convert it to energy to keep those things together. That's called the mass defect, just in case you wanted to know.
It only takes like that small.
Yeah. Is there a lot of energy in a nucleus? Sydney's saying yes. Do you have any evidence of that? I can think of 2 words that provide evidence of that. Yes. So therefore, if you broke that apart, what's going to happen to that energy? It's going to be released. What might those 2 words be?
I was going to guess nuclear bomb.
I was going to say Hiroshima and Nagasaki.
The second one I've heard.
Well, then you're aware of the second detonation ever. The first one was Hiroshima. Yeah. Okay. So yeah. So there is a huge amount of energy locked into the nucleus. Okay. So with all that being said, that was just bonus information, by the way. Let's do something with this. Anyone want to take a stab as to how we're going to find the average atomic mass? Or in other words, how are we going to find your grade in this class?
Honestly, I'd multiply the mass by the percentage
And then
I'd use the other one and
add them all up. And that's exactly it. So, the only mistake that students will make at this point, because obviously that's very easy, would you agree? About the only thing you can do to mess this up is to forget to convert your percent to the decimal form. Please don't forget to convert your percent to the decimal form. Okay? So just for example, what we're going to do is take our 34.969 AMUs. As someone said earlier, we're going to multiply it by the percent, add it to the other, multiply that by that percent. Boom, get your average atomic mass. So just for fun, just go ahead and do that on your handy-dandy little calculators that you guys have, and verify that you know how to do the process correctly by comparing it to the one that's already on the periodic table, or the one I already wrote up on the board up there. Okay, are you guys able to verify that? You probably got really close, if not exactly, the 35.453. Remember to follow your significant figures rules, and I can't remember how that turns out in this one. I don't know if it's going to go all the way up to the thousands place, I guess is what I'm saying. It does? How do you know? What was the result of this? 35.452. plus
Oh, no, no, but I got 26.
27 point what?
I got 26.1.
26 point what?
496.
Okay, and this one was?
8.956.
Okay. Pardon? Yes, yes. I mean, that's all right. Yeah. So it should probably go out to the hundreds place. Okay. All right. So obviously no problem, right? So I'm going to give you two more examples, one of which is going to be a different thing. I'm going to give you the same idea for the first example, and then I'm going to introduce you to a second thing. Whoops. And all I'm trying to do is put you in a position, places that you could screw up so that you don't make this. If you do make a mistake now, it's going to be a free mistake, and it's not going to cost you anything. You're welcome for that. So here we go. Next example. Does anyone know that element? Excellent. Oh, time out. Okay, there's that one. Try that one. And then I'll write the other question over here. Now, because, I mean, this is obviously a pretty easy process for you guys. However, as you all know, we've all made mistakes in entering values on calculators. And if you've done all of your work on the calculator for a test or a quiz, and all I see is an incorrect answer, you're going to get 0 points. But if you show the process and the setup, and still get the incorrect answer, but this process and setup was right, you're just going to miss 1 point. But we've already gone over that before. And I think you're going to find out for the second question you're actually going to need to do some work anyway. Ooh. Oops. Yeah, I was right. Anyone get a value for the first one yet? At 207.214, does that match up with the periodic table? Okay. Does that match up with the periodic table? So it matches up, right? Excellent. Okay, about the only thing, some of you may or may not have done that correctly because of this piece right here. I'm just checking. I warned you about it. Hopefully you took care of it, okay? Because occasionally it's about the only thing you can screw up. Now, what are we going to do with this next question? Okay, and where are you going to find that? Right off the periodic table, right. And from this point forward, every test that you take, you will have a copy of a periodic table available to you. It is not going to be the same copy as the one that you currently have. Pardon me? Okay, except for the element quiz. But the other two quizzes, you can have it available. You won't need it for the polyatomic ion quiz, but whatever. The ion quiz, you're definitely going to need it. But I'll give you that copy of that table later. Okay, so now, anyway, you look up the average atomic mass off the periodic table. Then what? And I know what a lot of you are going to be saying and thinking, but there's an easier way to do it. So what are you going to do? How are we going to find it? What is the average atomic mass for? What is that element, by the way? Rubidium. Very good. Look at you guys go. What is the average atomic mass of rubidium? 84.57? Okay. And obviously I have these masses over here of 84.912 and 86.909 AMU times some percentage, which we'll get to here in a little bit, equals that. Now what? I'm sorry? You tell me. No, seriously, you tell me. How do you know this? Which one's more abundant? Should be the 84. 84,912, 86,909, 85, 87. Is this right? Yeah, okay. I'll go ahead and write that, but okay. Now what are we going to do? And your first thought, although a good thought, will get you to the right answer, probably. There's possibly an easier way. Now what are you going to do? We need to know those percentages. We need to know this and that, because that's what the question is asking. Okay. What are you going to do? Don't just say, okay, so it'd be like me saying, find the enthalpy of a mixing sodium hydroxide with hydrochloric acid. Go.
Chemistry to find it out.
Use chemistry to find that out.
I would make each variable.
Such as? And like I said, your first thought, although it would work, might end up being a little bit harder than it needs to be.
Yeah.
Let's call one of them X, though. Which one do you want to call X? It flat out doesn't matter. You betcha. Because there's only two, and they add up to 100%. Would you guys agree?
Yep.
You should see the look on this young lady's face. Oh, yeah. Ready, set, go. Your brain's tired. It's only second period. Sulfate. No way. Did I mention that you needed to start studying those 4 days ago? You should start studying the polyatomic ions 4 days ago. I'm waiting for somebody to do the math on that one. No, you didn't even know about it until 2 days ago, right? Where I'm going with is I'm trying to instill a sense of urgency on you. The elements, you guys probably knew 20 to 30 of those elements anyway before you even started. I'm going to guess close to 20. Some of you may have had a little bit more knowledge than that. What's that? Oh, you knew more than that. That's going to be relatively easy. The ion quiz, although we're not there yet to figure that out, is also going to be just slightly more difficult, but not much. The one that is going to cause a problem, as I said before, is the polyatomic ion quiz. You're only going to be able to memorize a couple of those a day. I mean, to thoroughly know it. Because there's just really very little to go on there. You know, I think I gave you the hint about the eighth and the ith thing, didn't I? That's huge. The 8 and 8 thing is huge. But really, the rest of those, you got to learn the 8s. And those aren't easy. So you guys need to, even though I know that's not for like, what, 2.5 weeks or something like that, you need to start practicing that. Okay, anyone done with this other one yet? So as I believe it was Dominic said earlier, let's do algebra, which is what it comes down to. So we have 84.19 or 912x plus 86.909 minus 86.909x equals 85.468. At this point, what do we do? What's the phrase that you guys use in your algebra classes that you took 8 years ago? Combine terms and solve for x. So combine terms and solve for x. Yes? Good. What do you have? So what is x equal to? 0.722. And that is equivalent to, what does that tell us?
Well, 1 minus x.
No. What is x equivalent to?
The percentage of 84.
There you go. Percent of rubidium. And as it turns out, it is rubidium 85. I just wanted to make sure that you were clear on what that represented. So therefore, the other, what we're going to do is subtract that from 1, and that will obviously be the percent of rubidium. Anyone want to take a stab as to what the mass number of the other one is going to be? 87, because remember the mass defect. Okay. So she got 72.2%, which is pretty close. That's really darn nice. So rubidium 85 is 72.2%. The rubidium 87, therefore, is 27.8%. You guys pretty hunky-dory on that? Very good. I just wanted to show you the process. I feel like 10 minutes. How much time do I have left? 7? Okay. Can I get rid of this? All right. This next thing is going to help you for the ion quiz. I believe you all have had similar information before, but I'm going to make sure that we're all on the same page. Are you guys comfortable or familiar with the Group A designations on the periodic table and what they represent? Okay, well, I'm going to talk about a number of areas on the periodic table. Groups 1A and 2A, the Group A groups, and 3 through 8A are called the representative elements. The representative elements are the Group A elements. I'm going to use these phrases interchangeably, okay? The Group B elements are known as, does anyone know? Okay, those are the transition metals. Okay, the transition metals. Where are the metals on the periodic table? Everything to the left of this meter stick is a metal, with one exception. Hydrogen. Okay? We'll talk about hydrogen as the year goes on as to why most things put it here. It could easily also be here. Helium is usually placed here on the periodic table. It could easily be placed here also, but based on what they have a tendency to do, both of those elements, hydrogen is usually located here, helium here. But other than hydrogen, everything to the left of that meter stick is a metal. Okay? Metals have a tendency to do what when they form ions? Does anyone recall? Well, what are your choices with electrons? Either gain or lose. Metals have a tendency to, as it turns out, lose electrons. And if an atom loses electrons, what type of charge does it acquire? A positive charge. Whereas nonmetals, the handful that there are, have a tendency to gain electrons, and therefore when they form ions, they become negatively charged. So now it just comes down to how many are they gaining or losing, right? And that's related to, and as I think someone said this earlier, what do the Group A numbers tell us? Yeah, the number of valence electrons. Were you guys familiar with that phrase, valence electrons? Which are the electrons in the outermost energy level, okay? Metals have a tendency to lose those electrons. So, for example, all of the Group 1A elements have how many valence electrons? 1. They are all metals. Therefore, they're going to lose those electrons and form what charge? A 1+ charge. I don't care how you guys put this information into your brain, whether you need to write it down on either your notes or the periodic table that I gave you, which are yours to keep, by the way. You can do whatever you want with them. But all the Group 1A elements will form a 1+ charge. The Group 2A elements have how many valence electrons? 2. And since they are these metals? Yes. Therefore, they are going to lose those and form a 2+ charge. So all of the Group 2A metals will form a 2+ charge. Group 3A. Are they all metals? No, really only starting with aluminum. Okay? But anyway, how many valence electrons do they have? 3. Therefore, they're going to form a 3+ charge. We're going to skip Group 4A. Anyone want to take a stab why? Well, let's be specific. Carbon, metal or non-metal? Silicon, Well, have you guys heard the phrase metalloid or semi-metal yet? Okay. Anything that most anything that borders the stair-step or zigzag line is a metalloid. So silicon and germanium would fall into that category. However, silicon being above the line would have a tendency to be more of a non-metal. Germanium is also a metalloid, but would have tendencies to be closer to a metal. And then, as you guys are probably clear, tin and lead are clearly metals. Okay? So we're going to skip this group for now, except for tin and lead. We'll come back to that tomorrow. Group 5A, at least for the top three, these are how many valence electrons? 5. They are what types of elements? Non-metal, so they have a tendency to gain electrons. How many electrons are they going to gain? 3, because they're all trying to achieve, what's that? An octet, 8, right? So they'll gain 3, therefore their charges are going to be 3 negative. So nitrogen, phosphorus, and arsenic will form 3 negative charges. Oxygen, sulfur, selenium, and tellurium. Group 6A have 6 valence electrons. They're nonmetals, so they're going to gain 2. So these are all going to form a 2 negative. And fluorine, chlorine, bromine, iodine, and acetine are all nonmetals. Group 7A, 7 valence electrons. They're all going to gain 1. Therefore, their charge is going to be 1 negative. What about the noble gases? They already have their octet. They are not going to gain or lose electrons.